Okay, I think we'll start now. Welcome to IIT and to a bridge building lesson, if you'd like to call it that. Before we start, I'd like to give special thanks to IIT for hosting this, in particular Patty Cronin. Stand up, wave. Carlos Segre has been handling a lot of the bridge stuff for the last many years here. The two other people that are involved with this, John Callan is the IIT representative that handles almost all the logistics for the bridge. He and Carlo, he had some board meeting today, and George Krupa, who is our chief judge, is a professional engineer, bridge designer, unfortunately is down in Houston at this point. So we've got a somewhat brief history and types of designs of bridges. Let's take a quick look at this. When we talk about bridges, we're not talking about those in the mouth. We're not talking about teeth. We're talking about the type that support things. Amongst the first bridges, if you go way, way back, a twig or a branch or something like that where a bug could cross something. That fits our definition probably of a bridge. A way of getting across some type of something that is in our way. As things grew and objects got larger, the bridges got larger. So far these were all nature-made. Beavers are very good at building dams and bridges. They cut down trees. They make natural bridges. The Greeks were amongst the first to produce a record of bridges. There were probably other civilizations that did it before the Greeks, but the Greeks still have some surviving bridges from several thousand years ago. This is an example of one that is several thousand years old from that area of the world. The Romans enhanced the art of bridge building with arches and various and sundry structures over rivers or to carry rivers. The Roman aqueducts carried water. These bridges had water up here on the top. These carried the water across the dry land, actually you have a river going across a river here. That's the Roman bridges to carry pure water into their cities. Here we have a modern one. It's a canal over the River Dee. That's the canal up there. That's a riverboat going over the River Dee. Now you might want to say why. Well, the river gorge goes way down, comes back way up on the other side, and if you've got a canal that you could meet on either side there, how do you get the stuff across? You build a bridge so the canal that's up there at the top can go across above the level of the water in the river gorge below. There are several types of bridges. An arch bridge tends to be the nicest looking bridge, at least in my opinion. It's one of the nicest looking bridges. The arch bridge depends on a couple of things. It depends on having the end pieces basically tied in and the bottom structure here of the ground be solid enough so that as the forces are pushing down on this bridge trying to bend that out, the bottom structure of the bridge out, there's something there to prevent that. So this depends, an arch bridge depends on the strength of the supporting surroundings. Da Vinci did some work with military bridges that were built various ways. This was a bridge design that Da Vinci built depending on how long the logs were. His military could put these bridges together in matters of minutes. They had one of these bridges at the Museum of Science and Industry, I believe it was 2 years ago when they had the Da Vinci exhibit there. And I saw a group of 5 people put I think it was a 15-foot bridge together in about 5 minutes. And you could take it apart just as quick. Napoleon was another engineer. Napoleon wanted to be able to cross rivers for his conquests, but he had the engineers design the length of the bridge to cross the river, but he needed some standard measurement. So Napoleon came up with definitions of our basic units of length of meter, centimeter, and those type of things, mostly as a military aid, so that his engineers he could say, I need a bridge which is so long to cross this river to get at whatever I want to get to. And in fact, to this day, if you ever go to Paris, he posted official meters on the wall. There's at least 4, I believe, that are still surviving. It is a bar that's posted on the wall of a building, and underneath it, it says 1 meter. And you can still go to Paris and find an official Napoleon meter. A truss bridge. Truss bridges are easy to construct. They tend to be strong. They don't require any end structure holding them in because they can be set down on top of things. A lot of the bridges that we have around here are truss bridges. There is a website out there, IIT SMILE program. For several years had Professor John O'Leary from IIT here do the theory of structural analysis. You don't have to write this down. I got a handout here if you want to take and look up an analysis of truss bridges written on a, let's say, middle school, lower high school level. It tells why a truss bridge design can be exceedingly strong. You also have the suspension bridge. Now, the truss bridges, they were based on the fact that the end of the bridge, I should say the arch bridges, were based on the fact that the end of the bridge pushed in. The suspension bridge is based on the fact that the end of the bridge's structure out here will not pull in, will pull out, because all of the stresses here pulling down comes through the cables, and there's a tremendous tension on these ends here. If we go back to the arch bridge, there was tremendous compression holding them in. Suspension bridge, there's tremendous tension. It turns out that these can be made a lot longer than a lot of the others because you can run just basic cables. You don't need to have a solid structure there. Lately, last 75 years, I guess it is, they've also come up with a cable stay bridge, which I guess is a variation of a suspension bridge. And in this case, we have the cables, probably the nicest one. There's a new one in, all right, where'd my mouse go? There we are. There's a new one in Boston, and there's one across the Mississippi River down in southern Illinois. These tend to be very nice looking bridges. These cables support the thing, and all of the force is down on these pilings here. That's a cable stay bridge. Each of these types has a particular place where they could be used. And the design, whether it's better to have a particular bridge in one place than another type of bridge, a lot depends on where or what the circumstances are. You have movable bridges. Chicago is famous for its movable bridge. We've got a lift bridge here. They take the whole center span and lift it up so boats can go through underneath it. You have a swing bridge. Quite literally, the bridge swings sideways. So you have a swing bridge. There's one of these on the north branch of the Chicago River, I believe, that is still in existence. I don't know whether it works, but it's still up there. The more famous type of Chicago bridges are the Bastille bridges along the Chicago River. I think anytime they talk about this type of bridge, they always talk about Chicago. because of the types of bridges that they have there. All of these are movable bridges. They get out of the way of the boats. Again, some of these have particular designs that make them better than other types of bridges. If you go down here to the Chicago River, you'll find these are the types of bridges that they have across there. Unfortunately, once in a while, a bridge moves, but it's not intended to move. Some years ago, up in Tacoma, Washington, they built a bridge, 2,800 feet long. It's a suspension bridge, 2,800 feet long, 39 feet wide. The girders are 8 feet high, made out of solid steel. Somewhere I remembered that they were between 1 and 2 inches thick. There'll be pictures of this being built here momentarily. You've got, notice the size of that girder. There, that's 8 feet, and here's the cross members. Those are about 5 feet, solid steel. It opened. There was a little bit, being Tacoma Narrows, being up in Washington, there was some wind, but nothing terribly strong. And it opened, and it was called Galloping Gertie because it started to vibrate from the day that it was completed. And on November 7th, something happened. One of the mounting points let go, and the bridge started to do this. That is real time. That's not special effects. That's actually what the bridge is doing. For the teachers in here, the last few years that I've been showing this, the reason why I'm emphasizing this, the last few years that I've shown this, the students have said, oh, that's just special effects. No. You can do some stuff with special effects, but real time, it's somewhat more dramatic. That's solid cement. Oh, if you take a look at the middle here, what do you see? Yeah, there was an engineer out there. Imagine trying to take a sobriety test and walk the white line. That was an engineer out there looking at the bridge to see what could be done to stop the resonance. The problem was at the center point here, amongst other things, at the center point where the cable comes down and meets the bridge, one of the two sides broke loose. So it started to slide back and forth. In a minute, you'll be able to take a look. The wind was only about 30 to 35 miles an hour. It was not a very strong wind. That's why I say this is an unintended movable bridge. Notice the bushes down there. They're not blowing terribly hard. It's like you stick your hand out the car window sometime when it's moving and your hand starts to do this. That's the same thing that happened here with the bridge. Unfortunately, being steel, what happens when you bend steel and cement enough? What's it going to do? Break. This was, I believe it was about an hour, I forgot what the other time was, after. And if you notice the way that that water is blowing, it's not blowing terribly hard. There's not a really bad gale there, but it is a constant wind from a particular angle. A lot of engineering went into this bridge, but they missed one factor. What's the effect of a constant wind that catches the bridge at just the right angle? Okay. Interesting in these pictures, notice how much higher those end pieces are going up like this. Because what happens on a suspension bridge if you take all the weight off the middle? Those towers are going to bend out a little bit because there's not as much weight on them. That's out on YouTube. If you want to take a look at some more pictures of that bridge in particular, do a search on Tacoma Narrows Bridge on YouTube. And notice the comment at the bottom. It's not so much that they forgot to check their physics, they forgot to check all of the factors that would affect the bridge. So, okay, let me switch this. The next part that I'm going to do is how to build your own model bridge if you do this for a class project. We have some examples here that you can come up and take a look at afterwards. If you have any general questions along the way, please feel free to raise your hand and I'll try and answer them. If it's a specific question of some sort, I may ask you to hold off and see me at the end, okay? We're going to do a couple things here, and as was mentioned earlier, we have sort of a surprise presentation for you at the end. When we get there, I will ask that there be almost dead silence so you can hear what happens, okay? If you're going to build a bridge for one of our contests here, the first thing to do is read the rules, pick up the rules. There are copies of the rules up here that you can pick up on the way out. They're out on the website. At IIT, you can look up the current rules. They change in various ways from year to year to year. So read the rules. First thing you want to know is how big you can make the bridge. And then you have to design the bridge within what I call an envelope. And I've got 3 examples. There's really only 3 variations that we can have on this. Let's see if this, is that, okay. Why is this crooked? Okay, in this case, you have a given height, a given width, and what you do is you draw a rectangle with that height and that width, and here's the 2 support surfaces here, okay? We have a sample stand up here. This would be equivalent to those 2 support surfaces that are up on the top there. Thank you. You have to build a bridge so it touches that but does not touch anything else. One of the problems that we've had usually in the past is that the students will build their bridge either way too long or way too short. If we were to take, I'll give you an example in a minute. Let me go through the three ways of doing this. For this type of rules, where it's just straight across, a beam or a truss bridge. By a beam bridge, I'm talking about a bridge that is just several pieces like this, okay? The beam bridge has several pieces of wood glued together. If you've got enough height, that's not too bad. A truss bridge is really a beam bridge with a lot of pieces cut out of it. The second type that we have is a place where you have essentially the same size envelope, but you have to have a center clearance. You can't build anything straight across from one side to the other here. Okay, some type of a bridge, you need to have essentially legs on the bridge. I realize we're not talking about real bridges here. We're talking about the kind of bridges that you would build for a bridge contest at school, or that you would build for a science fair project. Something like that. A real bridge probably wouldn't, well, it would have to clear something in the middle, but it would have a continuous roadbed going across there. So in this case, it would say something like there must be a continuous clearance of X amount between the 2 support surfaces. So you would have to build your bridge someplace in there, okay? And then the third type adds a little bit more interest to it, because the third type allows you to build part of your bridge below the support surfaces. Here's the 2 support surfaces here. But you can have parts of your bridge down here. This is ideal for building an arch or an A-frame, because if you remember the arch bridge from the PowerPoint that I just did, the arch bridge wedges itself in, is dependent on how strong the surroundings are. If you were to take and build an arch bridge or an A-frame bridge and use it on that stand that we have over there, what would be the major part of the structure? The stand itself. So in that case, you would probably be looking at building an A-frame or an arch. So that's the three things. That's the first thing that you should do is you should draw a full-size drawing of that. Now, for the current rules, I drew a full-size drawing of that. And then I designed my bridge within that drawing. The one thing that I added to this is it tells you where it tells you that there must be a loading plane. In other words, a maximum level to have your support. So you should draw that on the drawing. And then design your bridge in there. This is a typical truss bridge. Lots and lots of triangles. Why do you want to use triangles? How many of you here have had geometry of any sort? Okay, a few of you have had geometry. What's the only rigid plane structure? A triangle. Triangle is the only rigid plane structure that there is. If you take a square, what happens if you apply a force to one side? You can tip it like that, right? Can you do that with a triangle? No. And in fact, some interesting things about triangles and about 3 points. What's the maximum number of bolts that they put on a jet engine on an airplane? 3. Because they can calculate how much force there is on those 3 bolts. How many mounting points are there on the space shuttle between the space shuttle and the external tank? 3, because they can count those. Think about, as a side note, think about that on a jet engine. Suppose that the jet engine decides to eat up a big bird. Not nice on the bird, but it's going to stop that engine. Which is better? To have the engine come off the fuselage or off the wing, or to have the wing come off? The wing comes off, it's really hard on the passengers, and it's not good for publicity. Whereas if the engine just comes off, and they can calculate with up to 3 connections. So that's why you want to use a lot of triangles on your bridge. So I designed this bridge to fit in the requirements that they have, that it span a 30 centimeter, 300 millimeter space, that it be no longer than 440 centimeters, no higher than 250, and the top of part of it is off there. And then I tried to make it look symmetrical. Symmetry is important. Neatness is important to building the bridge. Does everybody understand what I mean about, number one, using triangles? I could have extended this all the way up here and made it into an A-frame, yeah, but that takes a lot more material. How did I decide on how high to make this? I don't know, I guessed. You can guess. Now, there's a couple requirements on this. One of the requirements on the rules is that you have to be able to pass a piece of 2x2 through the bridge, which means the bridge has to be at least 2 inches high. Okay? So it had to be at least 2 inches high. And I wanted some space up above here that I could add some elements to keep it from swaying. Now, we're going to build it out of 32nd inch basswood. I don't know, for the teachers here, are you going to have your kids at least design and maybe build a bridge? Yeah, I see a lot of people nodding yes. You're going to get basswood like this, really thin basswood. Now, a couple things about this. It's really strong under extension. I can pull real hard on this and nothing's going to happen. What happens if I push on it? It bends and it breaks. It is fairly strong under compression. That's compression. If I take a short piece, it's much harder to make it bend and break. So what you want to do is the long pieces that you have that are going to be under extension, under tension, you want to make sure that they're good pieces of wood. If you're going to have some pieces that are under compression, you want to make sure that you brace them. If we go back to the drawing that we have over here, which part is under extension? Almost all these bridges, the bottom part here is going to be under tension. Okay, so we really don't need it that strong. I happen to make it that strong for other reasons. But where do I have to brace it to take care of the compression? Up here at the top. I had to brace that so the compression of this would not bend it. Okay. There are a couple other sample bridges over here that you can take a look at later. These were designed by some of the IIT architecture students. To various designs. The rules for these varied from year to year to year. So they're not all exactly the same. There is a couple of problems with particularly a bridge like this. How wide did we have to make it? 30 centimeters. Could not fall through the middle. If I take this bridge back over to my drawing here and I put it on there, what's it going to do if I try and put it on the support surface? It's going to fall right on through, right? That's probably why we still have these bridges around. They couldn't test them. So make sure that your bridges are long enough. Once you get the design done here and you've decided what to do, then you have to start working with the wood and the glue. What glue should you use? Turns out the best glue to use on wood is Elmer's Carpenter's cement for efficiency. Now, we're talking about efficiency here. We're not talking about total strength. We're talking about how strong it is for a particular weight. And the most efficient wood glue around is Elmer's Carpenter's glue, the sort of tan stuff that you get. Unfortunately, you can't get any really small tubes of that. But the small tubes of regular Elmer's glue work pretty good. If you're going for the ultimate strength, go for the Carpenter's glue. Crazy glue, jet glue, the fancy glues that they have are very, very strong, but they're also exceedingly heavy. And you have to get a special kind that works on wood. Yeah, I would, if you're going to do something like that with those kind of glues, only use it to make emergency repairs. Or if you're putting your bridge together on the way to school on the morning that it's due, then use jet glue, okay? Just don't get your fingers stuck to the bridge. That's real hard to test the bridge if your fingers are attached. You're going to want to cut the wood. Depending on what kind of joint you want to make on the wood, depends on how you want to cut it. If you want to make there are two types. If you want to make a lap joint, this is a lap joint. Let me use these two pieces here. This is a lap joint. Those two pieces cross over each other. It doesn't make any difference how you cut the end. Okay, if they're going over like this, you can just kind of cut the end however you want. A different type of joint is called a butt joint. It looks something like that. If you look at this from the end, the one is attached to the other. This is probably a slightly better joint than the lap joint, but it's also very, very difficult to make because what do you have to make sure? You have to make sure that this end exactly matches that. And then you have to put it under a little bit of pressure to hold them together. So my recommendation would be to use a lap joint, something like this. But then hold them together somehow. If you want to build an arch bridge, you notice what happened when I tried to bend this into some kind of an arch. What happens when I get to a particular place? It breaks. If you want to build an arch bridge, it's actually not too hard to do. What you need to do is you need to take hot water. Take hot water, soak the pieces in hot water. Well, start out with hot water, soak them overnight. If you're going to use 2 pieces of wood to make an arch, soak 3. Reason is, if one of them happens to break, you've got a spare piece. You can always use that other piece later. Then what you need to do is to take and pin them down, attach them to something. I've got a piece of wood here that I would use with some straight pins. This is an old drawing board. I would pin it down to this in the shape that I wanted to have it and let it dry. That works pretty good. You can actually make this stuff bend in fairly small radius. You know, you could have an arch bridge that looks like that by letting it soak, and that works. But be a little bit careful when you're bending it. You know, you have to pin it down. Total time for doing something like that, you have to let it soak overnight, and then you have to let it dry for a day, but that works. But again, make 1 extra piece in case one of them breaks, because you'll never ever get another set to come out exactly like that. Have your layout. I'm going back over to the drawing again. Have the layout, and then start putting the pieces together. In this case, I've done part of one of the bridges. I would put these pieces together like this. Okay. Right on here. Well, not quite right on there. I would put some saran wrap or some wax paper in between. Why do you want to put wax paper or saran wrap in between this and this? Because what happens when the glue dries? If any of the glue leaked out, what's it going to do? It's going to glue itself to this piece of paper here. Then you're going to have paper attached to your bridge, which is going to make it heavier but no stronger. So put some, we found that wax paper works the best. Saran wrap will work depending on the glue. If you're not using Elmer's glue, make sure you test it on the saran wrap first, that it doesn't dissolve the saran wrap. There are some glues around that will dissolve the saran wrap very quickly. Build a piece of the bridge. Okay. Take and, if you're building it like that, and then you want to attach another piece here, use straight pins or something to hold it in place. And then, if you're using lap joints, like I would here with just one piece on top of the other, just take and break it with your finger. If you want to cut it, use a single edge razor blade or a Zona saw. Emphasize single edge razor blade. I had one crazy kid come in one time with his fingers all full of bandages. What did you do? I was using a razor blade, and he showed me the razor blade. It was a double-edged razor blade, so he was pushing down on the top, on the sharp part. Not too swift. Okay, you get that in place, apply glue. Then you want to apply some pressure to the top here. You want to apply some pressure to force the glue into the wood. That's a very good use for your English or social studies books. Put the books on top of here. Let them be the, don't do it with your science or math books. You've got to use those for your homework. But your English or social, I apologize to any English or social studies teachers that are in here. Sorry about that, but they actually turn out to be the heaviest books usually, and that's what you want. Or get an encyclopedia. Or better yet, if you can pick this up after you get it slightly in place, and now I'm showing my age, get a spring clothespin. How many of you know what a spring clothespin is? Oh, more young people than I thought. I thought there would be about 4 or 5 of us in here that knows what a spring clothespin is. And put the clothespin on each of these to hold it together. That'll work too. Something to put it under pressure just for a short time so that the glue can soak into the wood. Okay, so that's gluing. Once you get the one side done, let it dry. In fact, every so often you have to stop for a while, let it dry. You might work on it for 10 minutes, let it dry for an hour. Come back for another 5 minutes, let it dry for an hour. Okay, so this is something, a bridge that is built might take you 4 or 5 days to do it, but you may only work an hour total on it. What's the rest of the time for? Letting the glue dry. After you get done with one side, leave it there. Don't pick it up, leave it there. Put another piece of saran wrap or wax paper on top of it. Build the second side exactly on top of the first side, so that you've got the two sides exactly the same. You might be off, let's say that instead of putting that side together like that, I was off a little bit like that. And then I come pick this up and go make the other side, and I'm off like that. What's going to happen when I try and attach those two sides? Are they going to go together nicely? No. So we've got, that's why you build one side right on top of the other side. Then what you've got is you've got two sides that are done. Now you've got to attach them together. On each of these bridges, this had one side done, that had one side done. What you need to do is find a place that's perpendicular. Okay, find a wall that comes up and or a bookend. Find two bookends or a wall and a bookend or a wall or something. Space them apart, put them up there, put a couple of pieces between them. What's the ideal number of pieces to keep everything in place temporarily? 3. So you put 3 pieces in there. Maybe one at each top corner and one in the middle of the bottom, or one at each of the bottom and one in the middle of the top. Let that dry, then pick it up and put in the rest of the cross bracing. Now, here's the bridge that I built from this. We take a look at this bridge. This took me, building time probably took about 2 hours. That's the time that I actually worked on the bridge. The other time to let it dry and everything took me about 3 or 4 days. So if you're doing this as a class project, it really needs to be done ahead of time. Don't try coming to school and hold it out the window to hope the glue dries while you're holding it out the window and driving to school. That doesn't work. For several reasons. If you're doing the efficiency of the bridge, you want to make sure that the bridge is as light as possible. This bridge lost, it weighs about 25 grams. It lost about 4 grams of weight. It lost close to 20% of its weight when the glue dried. And it takes overnight for Elmer's glue to dry. So do this ahead of time. I know your teachers always say, don't wait till the last minute, right? I used to do that, so I can't holler too much at you, except something like this you really have to do ahead of time. So once you get the two sides together, then, let's see if I can do this so that you can see it. Then you want to add some cross bracing. If I hold this on an angle like this, we've got cross bracing here and here to make sure that the bridge does not do this. I have some cross bracing on the end. Let's see how good the focus is on this. Oh, that's pretty good. I have some cross bracing on the end here to keep the ends of the bridge from doing this or bending sideways. Again, which parts of this bridge are going to be under compression? Which parts are going to be squeezed together? The top part. So that's where you want to have most of the cross bracing. Notice on the bottom there's very little cross bracing because these pieces are under extension or tension. Okay? So you don't need cross bracing there. You need a little bit on the top to keep those from coming together. You need something to keep the bridge from swaying. And that's why we have the end pieces here. Now, the basic rules for this year's bridge say, and I'm going to move over to the center table, say that you must be able to pass a piece of 2x2, standard piece of 2x2. And I'm driving the poor camera people crazy because they're trying to follow me. You have to be able to pass a standard piece of 2x2 through the bridge. Okay? That's one of the reasons that I decided on a truss bridge, because you've got to have the space to pass the wood through the bridge. You also, by the rules, needed to have two other spaces where the 2x2 would fit through from the top down and from the top down. Now, it depends on the particular rules that you use at your school. We tended to, at Morgan Park, where, Lee, you want to wave your hand? He's my cohort in crime from Morgan Park for many years. We did the bridge contest a lot there. We tended to make it easy and just say all that you needed to have was one centerpiece. Here, be able to place the weight or the hanger in the center. That made the design and the testing a lot easier. This year, they have two places, one on each side. And you have to be able to, let me see, I'll be right back. And it has to be able to support this plate. Notice this plate is narrower than the 2x2, which created other design problems. So we have to be able to place this plate in here. Now, if you're doing it at the school, it's up to your teacher to decide on what rules you want to use. In general, a 2-inch by 2-inch piece of plastic, 1/4-inch plastic or something like that, is sufficient to hold enough weight that it won't break, that most of the bridges will break. The last thing you want to do is weigh the bridge, because there's a weight limit on it. The two major places where we've had the most problems in building bridges is the dimensions. They built the bridge too short. The bridge would fall through. The second place that we had the most problems was the bridge was too heavy. If you buy the kits from here, you'll get 15 sticks. If you use 15 sticks and a lot of glue, you probably won't be overweight. If you start adding sticks to it, there's a good chance you will go overweight. This year, the weight limit is 30 grams. Some years ago, we took the heaviest kit. We weighed, what was it, about 1,000 kits? We were putting kits together for IIT. So we weighed close to 1,000 kits. We took the heaviest kit that we could find. We took a whole tube of glue. Well, back then we were using the Tester's airplane glue. Squeezed it out on a paper towel and let it dry overnight. We made the mistake of squeezing it out on the paper towel first thing in the morning, and we were real happy the rest of that day because it was drying in the classroom. And that came to about 27, slightly over 27 grams. Okay, so if you use Elmer's glue and only the 15 sticks, you're probably going to be okay. But how do you weigh the bridge yourself? You got to do it in grams. Can you borrow 30 cents from somebody? In nickels? That's the way to weigh. That is how you weigh the bridge. If you take this, it doesn't need anything but a meter stick. If you don't have a meter stick, any uniform piece of wood will work. This will work. Meter stick turns out to be a little bit easier to use. Take a pencil, balance the meter stick on the pencil. Okay, that's pretty good. Put the bridge on one end. Now, why do I say that it cost you 30 cents? A nickel has a mass of 5 grams. Don't think that you can take 2 nickels and replace it with a dime and you'll get 10 grams. No. I had one person that came in with this really chintzy little bridge, and they said, it was almost too heavy. I said, well, what did you use? He said, I used a quarter and a dime. No, got to be nickels. And what you do is you start putting the nickels out on the end here. There's 2 of them. That's 10 grams. There's 15. There's 20. There's, 25. So the bridge is less than 25. Okay? Now, if you've got a meter stick, each one of these divisions here is an additional gram. So if I put 20 out there, and I put this 10 grams over, that's 21. There's 22. do have to be a little bit careful. There's 23. It's almost 23. There's 24. I now get the fact that it's about 24, a little bit less than 24 grams. That's close enough. Now, the other day, about a day after I started building the bridge, I did this and I got 24.5 grams. I then went and got a 100th reading balance and came up with 24.46, which is real close to what I would get with this. But the official weight is what you get when you weigh the bridge at school. But if you want to know if you're too heavy, this works quite nicely. You have to ding somebody for nickels. Got to be nickels. Why nickels? How much? What's the mass of a nickel? 5 grams. Okay? And then you take and you test it. And I think in a minute or so, we're going to actually break this bridge. Yeah, we're going to break it, see how strong it is. But you're going to have, when we do that, you're going to have to be real quiet so you can tell when it breaks. Okay? I'll give you a couple. We got about 5 minutes here. Any questions? I'm open to any questions you want. Bridge kits are available either through your local hobby shop or from IIT here. IIT tends to be cheaper. The admissions office. Oh, great. I don't remember how much they are. So, yes?
I was going to ask, how are we going to break it?
Hang some weights on it. Okay. Lee, you want to help me pull that stand out? I'll show you how we're going to break it, and then you can ask some questions before we do it. Okay. No, leave it right on there. Which side has the hinged part on it? That side. So I want to do it this way. Now, if you're doing this in the classroom, hang on to that, there's a stool over there. If you're doing this in the classroom, a couple of things that I would suggest. If you don't have this type of apparatus, 2 tables that are set side by side that are the same level, use a bucket of sand. That works. Then the only thing is you have to weigh it afterwards. You know, and have somebody pour the sand in. We're going to clear the ceiling. And we put this up here because sometimes we will get a bridge that will hold a lot of weight and the pieces will fly out all over. Early on, I think when we were doing this the first time down at IIT, isn't it? I got the stand here. First time we were doing this down at IIT as a demonstration, we had a bridge that was maybe something like this, and people were sitting there like that, and the bridge broke, and it was a really interesting effect. A piece of the bridge went over and wedged itself inside a girl's coat like that. So there's this bridge sticking out from her coat, sort of like she had been stabbed by it. If you're doing this in the classroom, my suggestion is you only have 1 student up in the front here to work on this, okay? Now, in this case, we have to put this platform inside there and attach the bolt. The hanger, I think, is over in the corner. Now, I'm going to set this up there, but I'm not going to put the hanger on until I answer anybody else's questions that we have. Because once you start loading the bridge, at the national contest, somewhere on the order of 400 pounds. At our local contest at Morgan Park, we were, Akko, do you remember? He's one of my victims that did this at Morgan Park, right? Brings back bad memories, doesn't it? Okay. You're now teaching at Brooks, right? Okay. If anybody here is going to go to Brooks, you'll probably get Aku for physics, and you'll have to build a bridge, in which case you can blame me. The most that we've had hold at Morgan Park was on the order of, I think, 200 and some pounds. At some point, I had a picture of a student hanging under his bridge. He had built like a little seat of some sort out of a piece of cloth and thought that his bridge would be good enough and sat down on it. I originally had it posted on the wall, and when I retired, I think it disappeared. You know, for you back at the school, for the teachers here back at the school, you can get plastic if you impose, if you're going to do this, you could probably impose on, talk to Professor Segre here about borrowing one or two of the, not of the stands, but one or two of the holders and platforms here. Hold this while I get up there. I don't want to break it on the way up. The sad part is we do test these to destruction. I'll leave that off till I answer questions. Okay. Those of you up close here might, when we get to doing this, might want to stand up to see what's going on. I just lost my noise. Hello. Okay. Stick that back in my pocket. I bet that creates some havoc on the tape. This is videotaped. I believe you can probably, in some time in the future, for some nominal cost, get a DVD made of this. We're still trying to arrange that. Patty, do you know about what the arrangements would be if they want to? Okay. Email P. Cronin or just Cronin? Just Cronin, C-R-O-N-I-N at IIT.edu if you want a copy of the, if they make a copy of this. Okay. So, all right. Before we do this, and this will be the final thing, any other questions? You had a good question, how we're going to break it. Now you see, okay? Yes? I don't know. I have no clue. We're going to start out, I'm going to start out with one of these. Start one going around on that side. I'll let you grab a hold of this first, and then I'm going to pass it around. I'm going to start out with one of these. No. Okay. Pass it around up and down so that the people in the front row get to see it also. Any other questions? Yes? I have no clue. After doing this for all these years, I've predicted one thing and something completely different has happened, so I'm not going to even predict it. I would like it to hold 25 kilos, which is about 50 pounds, but, you know, because then what we do for a grade is to figure out the efficiency of the bridge, how much it held per gram. The highest efficiencies that I've seen have been about 5,000. An efficiency of 5,000 means that if you weighed 100 pounds, you could hold up a 747. You could walk under a 747 aircraft and pick it up. Yes?
I was going to ask, how much do these weights weigh?
That one is 5 kilograms. It's 11 pounds. I was going to say something else. Oh, the bottom plate is underneath my bag there. The bottom plate that goes across. Efficiencies have ranged as high as 5,000. what's the efficiency of a real bridge? Think about that while I answer his question again.
No, how would the thing work for that drop over?
I'm going to hang this, I'm going to hook this up there, and then I'm going to add weights until it breaks. And I want you to be real quiet so we can tell when it breaks. Okay? Yeah. There'll be a little snap or something like that. What's the efficiency of a real bridge? Our Chief Judge, George Krupa, builds railroad bridges for a living. And he took and removed all of the safety factors that he could think of from one of his real bridges that he built, removed a lot of other things that might affect it, and came up with a real-life efficiency for a railroad bridge of 5. How many of you have been on like the Dan Ryan or a bridge over the Dan Ryan and felt that bridge bouncing as other cars went by? Yeah, even a truck on that bridge will deform it a little bit. So, okay, you had one more question? Give me 4 of those and the rest 2s. Okay, did everybody on this side get a chance to? Okay, pass it down this way. Okay, any other questions? Okay, let me arrange some more weights here. I'm going to put on probably 5 of these, maybe. And after that, I'm going to go up by 2s. The hanger itself is 2, so we always start out with a load of 2. Okay. Now, if I were to do this in my class, that would be passing. If it holds the hanger, that you would get a passing grade. And I've had a whole lot that haven't even held the hanger. I had one, that's 2 kilograms, 2,000 grams. I had one bridge that looked so bad we started out in grams. It held, what was it, 25 grams? Not 2 kilograms, 25 grams, at which point it just sort of collapsed in pieces. Okay, does that look like you got most of the 2s? Okay, now here's some 2s here. Yeah, I know. Yeah, and there's 2s over there. I'll take those also. If you're doing this at the school and you're using this kind of weights, a few hints. Don't stack all the weights the same way. Don't stack them like this. Make sure that the students stack them at least at right angles, for the simple reason that if this thing comes down, these will fall off. And if they fall off onto somebody, it's not good. And usually what we do when we graded it, whatever was left on there, we took off the last one. So if it fell down and 2 of these fell off, we would take off the next one. Very carefully, the only injury that I ever had with this was one girl that had, what, 100 pounds on there? She had about 40 kilos on there, stacked fairly well up, and she saw it start to sway, and sway will kill the bridge. If you're doing a bridge break and you see it to start to sway, stop the sway by reaching in like this, okay, to stop it. If you're watching somebody else and they're your friend, tell them to stop the sway. If they're not your friend, you can let it sway. Maybe they'll fall apart. So. But what she did was she reached under it to stop the sway just as it broke. She wound up with these 3 fingers very flat on the end. Did not luckily hit any bones, but she did lose the, she lost what, 1 fingernail? 1 fingernail? Not nice. So, you know, never put your hand under this. Yes?
Did it go back?
Yeah, they grow back. It's just a little bit painful. So, okay. Now, we need to have you guys quiet. What was the original mass of this bridge? 24.46. Yeah. Okay. Somebody remember, somebody write down 24.46. Come on. Ooh. Okay. Now, I also want to, again, if you're doing this back at your schools and you're doing it on 2 tables where nobody can get really below it, you really don't need to do this, but just in case that top piece comes down there, well, that doesn't grab the top piece. This, so I'll put it here. This will keep the rod from tipping over, which is not good. So, okay. Yeah, and I think this gentleman here, if you could move back 1 row, please. We've never had them be too wild, but you know, there's always a first time for everything. So, okay. Okay, that's a total of 7 kilograms. It's about 16 pounds. If you're in the back or you can't see, please feel free to stand up. There's 12 kilos. There's 15. You got to be quiet so you can hear when it breaks, okay? There's 22. It's 50 pounds. Everybody hear that? Yes. Okay. Okay. 22 kilograms. I always sneak that one in. You notice it is obvious when it breaks, right? Yes. So we don't have to worry about thinking about it. All right. Who's got a calculator here? Okay, efficiency of this bridge. It held 22 kilograms, which is 22,000 grams divided by, what was its mass? 24 point. Who's got a fast calculator? It's 800 and something. Okay, two significant digits, 900. Efficiency of 900. That would place me somewhere probably in the top 4 or 5 at most IIT contests. Efficiency of 900, it would place me probably about the middle of the national contest. So the one sad part is you get to break your bridge. What I always like to do for my students is we would always take a picture of the bridge ahead of time so they would know what the bridge looked like. So, okay, any questions? I'm going to be around for a little while, otherwise I'm done. I thank you for being here.